Yeah, I'm okay. I'll click through here. It's not that interesting. Get excited though. Cool. So this talk is really about how I was able to get this data-heavy application up and running pretty quick, thanks to serverless, and in particular, one of the serverless frameworks for Python called Zappa. But before we jump into that, a bit of context on myself. So as Daniel mentioned, I'm working as a data scientist at Shopify. I've been there for about a year now. Prior to that, I was at Capital One with some of the gentlemen in the front here. For those of you that don't know, data science is a pretty interesting field. It's kind of an interdisciplinary field where you're basically solving different business problems using a mix of programming, math, and stats. And then the important part I want to get across here is, even though that is what I'm doing now, I don't have any formal computer science training or anything in AWS or DevOps or any of that. I studied chemical engineering, so I'm kind of a hack in that sense of how I've gotten into this. But the key takeaway is that through technologies like serverless, through simple beginner-friendly languages like Python, and frameworks like Zappa, I was able to get this thing up and running, and it works, so that's a plus. So hopefully you see this and you realize that, hey, I can do something like that too. I don't need this crazy background in tech or anything like that. Cool. So before we dive into the meat of the presentation, some context on the little situation we got going on in Toronto is required. So for those of you that don't know, apartments in Toronto are stupidly expensive. So we had a couple of people who knew Python, right? This is Pandas syntax. So Pandas is like a data analysis library, and Python is pretty popular. So if we look at the median price for a one-bedroom apartment in Toronto, it's sitting at a cool $2,200 a month. Well, this was actually when I made my slides in October, so it's probably gone up a bit by then now. So that's pretty shitty. So some people may say, hey, I'm gonna, I don't need a bedroom, screw it. I'll just do a bachelor, right? That doesn't work out that great either. $1,800 a month for median price for a bachelor apartment in Toronto. So that sucks. So people sink to an even lower level, no pun intended, and they'll start doing basement apartments. Guess what? Still $1,500 a month. So apartments are fucked in Toronto. Not only that, the whole process sucks. You're constantly looking at multiple sites. Because it's competitive, the listings go really fast. If you do actually get a listing and someone will show you the place, you'll be there with lineups of other people trying to see the place, so you can get competitive, you get into bidding wars. It's not great. So a couple years ago, I saw, do people read Hacker News? No? Okay, it's a good blog, or site, I should say. Anyways, this guy posted on Hacker News, and he posted this, pretty much what I ended up ripping off. It's a bot that scraped Craigslist, and it posted hyperlinks in Slack for him and his girlfriend to look at. So it gives them a feed of personalized listings. So I wanted to do that for Toronto. I wanted to build it so that other people could use it as well. So yeah, I will show you what I built. So this is called Domi. I think I Googled home or house in Latin, and that's what came up. So that's the context and why it's called that. And basically it's a Slack application. So it lets you set some preferences for what kind of apartment you're interested in, and it'll just send you a feed of listings from a couple sites I collect the data from. So I'll give you a little video demo of this to give you some context on what it is, and then we'll spend the rest of tonight talking about serverless and what powers it, and then some of the how I built some of the features. So the first thing you'll see is you go into Slack, and you get this onboarding message that tells you how you can set your preferences, which you do by going to this link. Here it's just a really bare bones web app where you can put in things like how much you're willing to pay, how many bedrooms you want. There's this map interface, so you can go and you can literally draw any arbitrary region on this map. And what I'll do is I'll save that in a database. and that'll only send you listings that fall within those areas. So I only drew one here. You can draw any number you want. At this point, you'll start getting listings to you sent on a regular basis. This went by really quick, but at any point, you can also pull more listings by just running this like don't pull command in Slack. So it'll give you any number of new listings you want. So you can see all those popping up in here. You can then interact with the listing. So I just clicked a button that said show me price rank information. So this is some details on like how well this apartment is priced based on what it is, and we'll talk more about that later. There's some other buttons, like I just clicked show me the description, so it populates that in Slack. I think I also clicked show all the images for the apartment, so you can see the other things it looks like. So the whole idea is you're not leaving Slack. You're getting this feed. You can go to the actual listing on the site from here, or in theory, you could just maintain this feed of listings in here. So hit upload at the end. I'm logging those clicks. I'm not doing anything with them right now, but you can imagine in the future, if you have a bunch of people on this platform and some of them are upvoting things and some of them are downvoting things, you can start to do things like recommend similar listings or give people personalized recommendations based on the types of listings they are liking to better tailor it for them. So that is what it looks like. So what we'll do today is we'll start with what's going on under the hood, which is the kind of whole serverless and Zappa part, which I imagine some people are interested about tonight. Then I'll tell you basically everything about how it works and highlight some of the packages I'm using. We'll do a deep dive into the price rank feature, which is hopefully interesting for people. When I originally did this talk, it was at PyCon, and it was in like the, I don't know what you call it, like the machine learning track, so that's why I have this part in here. So it's a bit more technical, but hopefully I'll be able to explain it in a way that makes sense. I have a couple new sections that I haven't presented before. So one is about a different form of application monitoring using this Python package called Great Expectations. And then I'll end off with like a bunch of weird shit I had to deal with serverless. So cool. So I'm assuming most people have heard this spiel before about serverless, given this is a serverless meetup, but I know there are some people who are new to this, so I will go through it. So the whole idea with serverless, it does not mean there's no servers. There are still servers. There's just no servers that you have to manage. So you don't have to worry about turning on new ones and turning them off. You don't have to worry about applying OS updates and software patches. Instead, you just write code. And you invoke that code on demand in response to different events. So the simplest one could be like an API endpoint is called, and then your function gets triggered. Another one is a new file gets uploaded to your cloud storage, and each time a file gets dropped there, you want to kick off some type of code or reaction to that event. Or you can just do it on a predetermined schedule. So you can literally have like cron jobs, which I'll talk about later. I'm literally doing that with this. And there's a bunch more stuff you can do. And pretty much every cloud offering will have one of these. I'm using Amazon Web Services. No particular reason other than I used it at my old job, so I had a bunch of familiarity with it. That and Zappa actually only works with that. So I picked AWS first, and then I found out about Zappa. They weren't linked together, but if you do want to use Zappa, unfortunately, you can only use it with AWS as of now. Right, so straight from the AWS Lambda homepage, which I learned from Daniel is like 5 years old now. So AWS was the first one, like most things cloud, they were the first ones to release a serverless offering. So if you go straight from their homepage, run code without thinking about servers, pay only for the compute time you consume. So no hassle with servers, and it's cheap, which is important for me. So I don't make money off this. Very good for side projects. So Amazon or AWS has a free tier. You'll notice from the screenshot, some of these say 12 months free, right? So if you want a server on Amazon, you spin up an account, you'll only get this like tiny server for free for a year, and then you'll start paying for it. Lambda is always free. So what does that get you? You get 1 million requests and 400,000 gigabyte seconds per month for free. So if you put that in more concrete terms, you could run a Lambda with 250 megabytes of RAM for basically 2/3 of the month for free. So if you think about a dinky little web application that's like only serving users in a single time zone, that's pretty much all the compute time or runtime you need to basically have a web application running for free forever until they change their terms. So please don't do that, Jeff. Sweet. So we think about like what do I need from this? I want no knowledge or maintenance of servers. I don't want to think about that. I just want to write code, so it checks the box there. I want to be able to run periodic batch jobs to grab all these listings, which we'll hear about later. So we saw that you can invoke lambdas on a regular schedule, so that covers it for me. I want to be able to respond to API requests, like serving a web page, covers that. And the last thing I want is cheap and easy, cover that, and support rapid development, iteration, and deployments. Serverless doesn't do this for you out of the box. You need some type of framework that does that, so that's where Zappa comes in, which we'll talk about. So serverless is awesome. Cool, but in order to understand Zappa, you need to understand what life is like without Zappa. So to do that, we're going to walk through what serverless Python looks like from scratch. Can you read the screen? Is that okay? Make it bigger if not. It's not too important, it's not here. So, simple use case, let's periodically download some data and save it to cloud storage, so that's 3. To do this, you basically, if you're developing locally, you'll use pipenv. It's like a package manager for Python, similar like npm if you're coming from the JavaScript world. So you install requests, which is a library for making web requests. Every Lambda function you have for Python, you have to define this handler.py function where you have your imports, and then you have a handler function. So this function is the entry point when your Lambda function gets invoked. This function will get run. So you can see I have this really important function called do stuff, where stuff happens. Here's what my directory would look like on my local. So I have some pip files, those are created by pipenv, and then I have my app folder where I have maybe 2 Python files, right? So the first step you need to do is you need to build a deployment package. So all AWS Lambda gives you is they provide you a Linux environment with Python installed. So if you want anything else, if you want any other packages, you need to upload those for your functions. So to do that, you need to figure out where all your packages are stored on your computer. You then maybe set some environment variables in your bash script to tell you where those are stored. You'll then zip all those up into a zip file, and that will be done for that. The next thing you need to do is create identity and access management roles. So in AWS, you use IAM roles to dictate things like what your application has access to. So for our use case, the IAM role will describe all the other Amazon services or their permissions for our Lambda function. So there's a bunch of steps you have to do here. First, you have to create the role, specify this thing called the trust policy, and then attach it, give it new permissions where you say, hey, I want my Lambda to be able to write or do things with S3, so that's Amazon's cloud storage service. I want my function to be able to write to cloud storage. I also want it to be able to write the logging service so I can understand if stuff is breaking. Finally, with all that done, we can create the Lambda function. I should have mentioned all this is happening. Amazon Web Services has a CLI, which is actually written in Python, fun fact. So you can do all this stuff from your terminal. So I'll create my function, specify things like the what version of Python I want, what memory size I want, et cetera, and then the final step after I've done all that is I also need to add CloudWatch events to trigger my Lambda function. So you can think of these as like the cron job setup. CloudWatch is a service in AWS where you can specify rules to do things on a schedule. There's probably a bunch of other stuff that it does that I'm not aware of, but so I was using it. So again, more AWS CLI commands to create these rules and this CloudWatch event. Finally, we're ready. All that's there. We test it out. And we run it, and you get an error. So, unable to import package main. So, not sure what's going on there. Sweat a bit. Start Googling on Stack Overflow, and like the 4th post down, you'll find your solution, which is has to do with like file permissions, like something really stupid. But it's annoying, right? These are the things you have to go through if you're doing this from scratch. So you need to properly set file permissions such that, I forget what, but yeah, run this Linux command and do that on all your files. Rebuild the deployment package, update your Lambda function code, try it again, and it works. So not too bad. Do it the first time, you know how to do it. But let's change our use case a bit. So say instead of saving to cloud storage, we want to save it to a database. So I'll install psychopg2, which is a Python library for interacting with Postgres-based databases. So I'll do that, go through those steps again. So I'll read my deployment package, update our Lambda function, pray it works, and you get an error again. So in this case, it's having trouble importing this new psychopg2 package. Why is that? So after doing some reading about this, like can't import function X or package X on Lambda, you'll quickly learn that Lambda functions run on Amazon Linux, so a different version of Linux, and any of these Python packages that have compiled dependencies will not work. So if you install them locally and they compile with your Mac OS or Windows, whatever you're using, and then you try and copy those onto Linux or Lambda, it will not work. So you need to get these libraries pre-compiled for Amazon Linux. So luckily for us, there are some places where you can go and you can just download these and you can take these versions and stick them in your deployment package and you're done. Or there's Docker solutions available. So yeah, like this article, the title of this article tells you how bad the problem is. Like how to claw your way out of AWS Lambda function hell using Docker. Right, so this is really a pain point for Lambda. So with this Docker image, how it works, excuse me, is the Docker itself has the Amazon Linux on it, image. So you'll install all your dependencies in there locally on that Docker, and then you copy them out and upload them for your deployment package. So not great, like quite a bit of work to get around all these kinks and intricacies, especially for the first time. So with that, let's talk about Zappa. How many people here have heard of Zappa, by the way? Well, okay, yeah. That if you actually go to the README, that's like the logo is the musician. Cool. So no one's heard about it. So Zappa is like one of a couple serverless frameworks like specifically for Python. I think it was the first one. I'm not 100% sure. But if you go straight from the README, it says Zappa makes it super easy to build and deploy serverless, event-driven Python applications, including but not limited to Whiskey web apps on AWS Lambda and API Gateway. So Whiskey web apps is, I actually don't know what that stands for. I think it's like Web Server Gateway something interface. Anyways, if you guys have heard of Flask or Django, they both use this. So Zappa makes it super easy to take existing like Flask web apps or Django web apps, and you can literally just deploy them straight onto AWS Lambda. You don't have to change a thing. It is literally magical. But you can also do other things, which I'll talk about. So let's take our exact same use case from before. So periodically download some data, save it to the database. So we go through the same steps again, where we install our two packages. The only difference here is we're installing a new dependency. So pip installing Zappa. Next thing you have to do is create kind of like a config file. So this is a JSON file, and you can create it with Zappa init, but it basically, we'll go through this more later, but it basically specifies a bunch of stuff about how you want your function configured. And then you go Zappa deploy dev, and you're done. It's up. I'm not doing a demo because I don't have my computer, but when I did this at the Python meetup, I demoed this, and like you can find examples on the internet, and like you can get a live web app on AWS in like 10 minutes if you've used Python before. So it's really quick. So let's unpack kind of what went on behind the scenes when I called Zappa deploy dev. First, it takes care of that like annoying deployment package process I walked through, like figuring out where all your packages are, zipping up all the code, setting the file permissions properly. It takes care of all that for you. What it also does is it will recognize whenever you have one of these packages that has these it has compiled C dependencies, and it will swap those out. So it'll swap them out with packages that are pre-compiled for Amazon Linux, so you don't need to worry about that. All that annoying stuff I showed you with like IAM roles and permissions and all of that, it does all that for you. It makes all the IAM roles for you, it makes the CloudWatch events for you, it creates a Lambda function for you, it does all that. So it's pretty great. What I didn't talk about with all those examples, so those were just like probably the simplest version of a Lambda function, which is just running some code on a schedule. As soon as you get into web apps, there's even more stuff you have to do. So you have to create like an API gateway resource. You have to figure out a way to map the gateway request to the Whiskey framework in order to make it work with your existing Flask apps. If you want to have a custom domain, you'd have to do a bunch of stuff. I don't even know what you'd have to do. Zappa just did it for me. So that domain.cloud domain just points straight to my Lambda functions. So quite a lot of stuff it's doing, which is pretty great. There's a bunch of other awesome features associated with it. So one is it lets you view logs in your terminal from your function. So I can call Zappa tail dev. So dev's the name of like the function, and that spits out all my logs for me. You can do other cool stuff too, like hey, show me all the logs from the last minute. Show me all the logs from the last day, and only show me like the error messages, for example. So you can parse and filter logs there too, which is pretty cool. Another really useful thing is you can do remote invocations of code from the command line. So here I'm calling Zappa invoke dev, and then I have this string which is just Python code, and it's literally executing this Python code on the Lambda function and then printing the results on my console, which is, I don't know if that seems impressive, but it's like incredibly useful for when you're trying to debug these things and like figure out if your environment's set up properly in your Lambda function. Other cool stuff. There's some intricacies with Lambdas where on some requests, AWS needs to re-provision a container with your code before it can process the request. And when that happens, the response time goes way up. So this is a known problem. It's called cold starts, right? So it's Amazon, the first time you get a request, they need to get down all your code and put it on a running container that can then respond to the request. So the loophole or the way around this is you basically ping your Lambda, I don't know what it is, every couple minutes, and that keeps it warm. So that makes sure you always have this container ready for requests. So Zappa takes care of you, it takes care of this automatically for you. So the default setting is keep warm true. So by default, you'll just have a CloudWatch configuration set to ping your Lambda every like 4 minutes or something like that. Another really cool thing, so AWS, for Lambda, your deployment package cannot be more than something like 50 megabytes. So there's a bunch of popular packages used in the data world for Python. Pandas, NumPy, SciPy are a few of them. These are all like 50, 75 megabyte packages. So as soon as you have these in your project, you'll immediately go over the limits. And Zappa has an awesome way around this. So they have this setting called Slim Handler. So what Slim Handler does is it will take the larger parts of your deployment package and upload them to S3. Your deployment function that gets uploaded to your Lambda is just like a minimum, smaller deployment package that just has like the Zappa dependencies. And then what happens is when your container or Lambda function is being invoked for the first time, it will grab that bigger zip file from S3 and unpack all the contents to your temp directory. So then you can just import your packages. So this is like a really smart way they got around the deployment size limit. Since then, Lambda's introduced new features like Lambda layers. I don't know if you guys have heard of layers. Lets you kind of save a bunch of different deployment packages and be able to import them. So it kind of gets around that as well. Zappa doesn't support this yet, so you have this to work around with. It does add a bit of extra startup time because your Lambda function has to download 100 megabyte or more zip file and then unpack it. So we'll talk about that a bit more later. But it's okay for a one Lambda function because you only do that once. And there's a bunch of other stuff, so I won't talk about this. Go look at the repo if you're curious. Or to talk about other serverless frameworks. So when I was looking at when you Google serverless frameworks, this one will come up, serverless. Probably the most popular one, I think. People can correct me if I'm wrong. I'm pretty sure it works with all the different cloud providers, which is nice. The downside for me was I didn't want to touch anything JavaScript. And I don't want that to take away from this. Like, I haven't looked at this much. I'm sure it's a great framework. I'm sure it's really easy to use. It may even have more features than Zappa. For me, I wanted something where I didn't have to worry about installing a new JavaScript like package manager. If there was errors, I wanted to be able to go in and read the code and actually understand what was going on. I don't want to figure out JavaScript for that. So that is why I went with Zappa. Do not immediately just default using Zappa because of this presentation. Do your homework and figure out what makes sense for you. The other kind of Python, or the only other Python serverless framework I've come across, at least for AWS, was something called Chalice, which is built by the Amazon team. With Chalice, they've like created a new web development framework, so you can't use Flask or Django. You have to use their new thing they built, which is really annoying. And then immediately I was like, no, I'm not going to use this, because as soon as you like don't want to use serverless anymore, you'd have to switch everything. And you also lose, like, tons of people have spent years building functionality into Flask and Django, which is really good functionality, and you're just losing all that by building a brand new thing. So they probably have good reasons for doing it, like speed and stuff, but yeah, anyways, that's another one out there if you want to check it out. Okay, downsides. Zappa does not come without its downsides. So the biggest white elephant in the room, at least when I've talked to people, I don't know why I said white elephant. It's not even an expression. It's just elephant in the room. The biggest elephant in the room is that Zappa, people are worried about, is Zappa even being maintained? And it's a good question, because this guy who built it, his GitHub handle is like Miseru, I think his name is Rich Jones. He was like the guy driving this. And so you can see all the development activity in like 2017, 2018. And then basically last year, it just drops off a cliff. So there's essentially no development activity. So a lot of people are curious about, like, hey, is this thing still being maintained? What's going on? The answer is it is still being maintained. You can see activity is picked up. They were just deploying merging a bunch of changes and some patches. I cannot say that it's undergoing like active feature development. They have a really active Slack community, which is great. So if you do want to use this, there are a ton of people. There's like, I think 4,000 or 5,000 people in their Slack channel you can go and just talk to. And there's been, before I was giving this presentation, I was kind of asking, like, hey, I want to address this elephant in the room, like, is this thing being actively maintained? And there are a couple of people working on it. So slowly but steadily, I do think development will pick up again on this, but it's definitely nothing compared to like serverless and one of those big frameworks I showed before. Vendor lock-in. If this works with AWS, if you want to switch to another cloud provider, it will not work. It could, in theory. It's open source, so you could go in and build it for Azure or any of these other cloud providers, but that would take a lot of time. So that's one. Other things I talked about, doesn't support AWS layers yet. There are a bunch of open PRs where people have added a lot of this functionality into Zappa. They've just been waiting for the maintainers to get to it. So I think that'll be coming soon. And then the support for precompiled dependencies will get better. So those are the main downsides that I've come across. Cool. Do people have questions at this point? I'm happy to take those, or we can do it at the end. Okay. Oh, right. Okay. At the end, no questions. Cool. Well, let's dive into Domi, and I'll tell you everything about it. So everything I have circled on the screen here is powered by Zappa. So all of those, black hexagons, six sides, yeah. Those are Lambda functions. Or I can just use my mouse. This guy is API gateway, so mapping requests to my Lambda functions, that is covered by Zappa. This is the logo for CloudWatch, that is covered by Zappa. So most of everything you see on here is taken care of by Zappa. And what this looks like, all right, probably. doesn't matter, you can read it. This is just a settings file, so I have a bunch of configs in here that say like, keep this warm because this is my application function. I want this to be snappy and responsive, so I want it to be hitting it every 4 minutes to make sure it's not going through those cold starts. I have my custom domain in here, so there's where Zappa automatically takes care of that for me. Yeah, Python version. So pretty basic stuff. So that's what that looks like. So first step in Domi is I need data. So I go out to a bunch of different sites and I pull down the listings from there, and then I save them to a database. So this is what's really cool, I think, about Zappa is it lets you have this mix of like, hey, I have some functions where I just want to run them on a schedule, or hey, I have this web app, I want this thing to be mapped to this domain. There's lots of flexibility. So I have all these different Lambda functions. So each thing in this, or I guess each key in the config maps to a different function. So this is a different function I have running in US East 1, and you can see I have all these different, essentially cron jobs, you can think of them, right? So I have all these functions that will get invoked on these schedules and run on this Lambda function. It's pretty straightforward. What we need to do next is save our listings in a spatially aware database. Why spatially aware? So we can do that map stuff I showed you before. So that is all powered by something called PostGIS, which is an extension for Postgres. So both open source, you can use them today, you could get it up and running locally if you wanted. And what PostGIS does is it adds support for geographic objects. So it allows location queries to be run in SQL. So, for example, I want to return all listings that fall within a region a user has drawn that I've saved in the database. So exactly what I showed you in that video, this is accomplished by the SQL query. So you have your kind of your spatial constraint, and then you have your other constraints, like it needs to have this many bedrooms and bathrooms. On the Python side, you do this using the SQL Alchemy package, the SQL Alchemy package is what you use for interacting with databases. It's an ORM, but if you want to do that with PostGIS, they have a extension called GeoAlchemy too. So you can see here I'm setting the data types for those geometry objects. And then just very similar to SQL, you can use their Python API to write your queries. So you can see here, there's a very similar syntactically looking statement to do the location filtering you saw before. And then we serve to users. So two pieces here. One is another kind of scheduled job where the CloudWatch event invokes a Lambda function, pulls down listings for users based on their settings, and sends them those listings in Slack. But you also saw there was interactivity, right? So anytime I was clicking those buttons, like show me the description of the apartment, show me images, show me the price ranking information, those are all calling my Flask web app. So that's also handled through Zappa, so that I'll go through, uses the Slack API, the Python package for that as well. So that all gets fired to my application function, which will interact with the database to pull that information. Cool. So that was a really quick overview of how it works. It's really not that complicated. Just a bunch of different Python functionality that does those operations. One of the more interesting components of it, I think, is this thing called price rank, which is, you saw an image of it earlier in the video. So what I want to do now is tell you a bit about, well, actually pretty much tell you everything about this feature, from the underlying theory for how it works, the different options I went through, and then how I'm also showing it to users. So the whole motivation for this, actually, the real reason I built this is I wanted to get into the data science track at PyCon, and my talk was very like Python and computer science. So I was like, I need some machine learning model in this. So that's kind of why I built it, but I do think the feature actually adds some value as well. So the whole idea is, yes, everything, and if you talk to any other person in Toronto and said, I'm paying $2,200 a month for my apartment, everyone would say, yes, that's really expensive. However, certain apartments are more expensive than they should be based on what they are, and vice versa. So the goal of this feature is to say, given what this apartment is and the attributes of this apartment, is it priced, is it in line with expectations, is it priced too high, or is it priced too low? And in order to do that, what we need to do is get an expected price distribution based on the type of apartment. So most machine learning models will predict the expected value, or the most likely value, or the mean. So they'll say, given this apartment, or instead of saying, I think this apartment will be priced X, which is what most machine learning models do, we want to say, this apartment will be priced between Y and Z, or all the apartments will fall between Y and Z like 50% of the time. Given that this is like a 1-bedroom, 1-bathroom apartment in downtown Toronto, what is the expected price range of apartments in that area? So that's the problem we're trying to solve. And once you can predict this distribution of prices, it's fairly simple to say whether something is priced high or low by looking at where it falls on the distribution. So the first thing I went through was clustering. So clustering is an algorithm that groups together similar points based on their proximity to each other. So these are just arbitrary axes, but you can imagine this being like bedrooms and this being like bathrooms. And what you can see is these clustering algorithms are automatically assigning similar points to a group, right? So we can imagine everything in this P group is a group of similar apartments. So once we identify what group an apartment falls within, we could look at the prices of all of those apartments and come up with that pricing distribution. And then we just use that. The downside of this approach is that it treats all the different variables you cluster on as having the same impact on price. So what I mean by that is you could have 2 apartments that are very similar. They have the same number of bathrooms, they're in the exact same location, say they're both furnished, they're similar size, but they have a different number of bedrooms. So a clustering algorithm may say, hey, these are really similar except for that one thing, but I'm still going to put them in the same cluster. But the problem is that one thing that they're different on is the biggest driver of price for apartments, the number of bedrooms. So that's where this falls apart. There's not an easy way to handle differing impacts of variables. So we moved on to the next option, which was linear regression. So linear regression is one of the simplest types of models. It lets you predict, again, the average or expected price based on a combination of different parameters. So the key is that it's giving us the average or expected price for a given type of apartment. So the most likely value. Again, we want the distribution or the range of values we could get for that apartment. So in order to do that with linear regression, you can basically use the you can estimate the variance of the residuals. You use an assumption of normality, and then for a given prediction, you can get a confidence interval around that. So pretend, very unrealistic, but pretend X was bedrooms. So we could say, hey, for this 18-bedroom apartment, this would be the average expected price, and then again using the residuals to calculate the variance, we could come up with like a 95% prediction band. So where do we think 95% of the prices would fall? So this works, however, the calculation of that prediction interval and the way I just described relies on something called the Homoscedasticity Assumption. So what this does is it says that the variance around the regression line has to be the same for all values of the predictor variable. So pretend we're talking about bedrooms again. The variance in predictions has to be the same for all of these. So if we look at a quick graph where I'm plotting pricing distributions by number of bedrooms, you can see that as the number of bedrooms goes up, the variance widens or increases. So right away that assumption gets broken and we can't use that. So went on to a third option, which is the one that ended up being used, and this was quantile regression. So linear regression helps us predict the average of a distribution. What we ultimately want is a method that lets us predict other properties of a distribution. So that's what quantile regression does. it lets you predict like the 25th percentile or the 90th percentile or the median, the 50th percentile of a distribution. And once, and again, it's similar to linear regression, as you can like put in a bunch of different variables to figure out how these quantiles will change with them. So you can see this red line would be like your linear regression line of best fit. So it's saying like for this given value, I think it's going to be here, which is great if you're trying to predict what's the most likely value. But if you want to predict how wide the distribution is, where will 50% of my points fall, that's where you need quantile regression. So what we do is we basically fit two different models. So one is a model to predict the 25th percentile. Another is a model to predict the 75th percentile. And then from there, it's pretty straightforward, right? For a given set of apartments, we can predict the lower and upper bound for where 50% of those prices would fall within. And then using that, you can say, hey, if the price falls between P25 and P75, I'm going to call that typical. Falls below that, I'll call it price low, and if it falls above that, I'll call it high. So that is it's kind of like a fundamental theory for how this works, but in order to get a good model, you need to feed it a bunch of data in a smart way that tells it about the price. With any type of thing, you start with a bunch of features. So these are all different variables that impact price, as you could imagine. So bedrooms, bathrooms, how big is it? Is it furnished? All those things, as you can imagine, would have some influence on price. Another big one that has influence on price is location. But this one, from a modeling standpoint, is much harder to encode or feed into your model. And what I mean by that is location is typically encoded in latitude, longitude coordinates. And you cannot just take these two coordinates for a given point and throw them into your model, because that means nothing. Your model is looking for some linear trend. So it's saying, like, hey, if we move this direction in space, do prices go up or down? And that doesn't hold true. Maybe there's some city where if like you go in one direction, prices always move in that direction, but that's not the case, right? Cities are messy. There'll be random pockets where prices are really high. There'll be pockets right beside that place where prices are really low. So you can't just feed that in your model. So what you need to do is find a way to encode area or location into your model. So a simple way is you could just call the Google Maps API and get the neighborhood, and then you could encode the neighborhood into your model. I'm cheap. I didn't want to pay for Google Maps API, so I used an algorithm to just produce neighborhoods, because neighborhoods are arbitrary, right? Someone decided we shall call points in this grid, neighborhood X, right? So it doesn't really matter what the neighborhood's called. We just need some way to encode this. So I use this clustering algorithm to basically come up with neighborhoods for me. So you can choose how many you want. So this is what the output of that looked like. And then what we do is we encode those. So if an apartment falls, we'll call this cluster 0. If an apartment falls in cluster 0, we put a binary indicator. So we put a 1 for cluster 0, and that informs the model as like, hey, this apartment falls in this area. And when you do that, your model performance goes way up, as you would expect. Location is a big driver of price, so it makes sense that feeding your model information about where the apartment is will give it a better predictive power for determining what the price is. But there's problems with this approach. So just like a city planner who's deciding what neighborhood is which, the algorithm has to do something similar, right? At some point, it has to draw this arbitrary decision boundary where it says, as we move across here, it's all of a sudden going to start saying you're falling in cluster 0. Oh, you're now in this cluster, right? So if we zoom in even further, you could run into scenarios where you have 2 points that are literally across the street from each other, but this algorithm is saying, nope, you're in this cluster and you're in this cluster. So it's treating them as completely different points or areas, even though they're pretty much the exact same area. So a much more flexible approach for handling this is something called nearest neighbors. It is a very intuitively named algorithm because it's literally doing exactly what the name says. It says for a given point, find me all of the closest points, right? So how we can use that is we can say, hey, for a given apartment, find me 50 of the closest apartments that have the same number of bedrooms or whatever. And then we take all those apartments surrounding that apartment and say, calculate the mean or median of that. And then we can feed that into our model. So to do this, I used a package called Annoy, which stands for Approximate Nearest Neighbors. Oh yeah, that's a pretty great name. How many people use Spotify? Hopefully a few. So like your Discover Weekly or like Song Radio, a lot of people surprisingly don't use Spotify, but there's this feature where I think it's really cool. You listen to a song and you literally hit go to Song Radio, and then it just plays similar songs to that song. So really neat. So Annoy is what they use to find similar songs. So it's a library that lets you do really, really fast searches for nearest neighbors. And this is a really important problem for them because they have to search this massive vector space for all these possible songs that could be related. This is complete overkill for my needs, right? There are much simpler algorithms you can use. Scikit-learn is a popular machine learning library, so they have implementations of nearest neighbors you could use. Why did I use Annoy? I wanted to eventually do more complicated nearest neighbor lookups to find similar apartments for recommendations. So you could feed in like images or text or all these other things. And that's where Annoy really shines, is when you have a lot of features for your apartments or your vectors that you're trying to do similarity on. That's where Annoy really shines. So I was using it as a proof of concept, never got to the stuff I eventually wanted to do, but that's why I chose it. The API is really simple to use. I think this is straight from their README on GitHub, and I've modified it for my uses. But basically, what you do to use this package is you build up this index where you basically feed it all the points. So I'm feeding it every apartment, and for each apartment, I'm telling it the latitude, longitude, and number of bedrooms. Then all I do is if I say, hey, for this apartment 1, find me all the nearest neighbors. It's literally just this single API call. So give me the 50 closest points to this apartment. So it's searching that vector space and finding them. And then what you do is you'll do a join back to your database, and you'll figure out what were all the prices of those 50 nearest neighbors, and then you'll calculate like a mean or a median, and then you just put that into your model, right? So this is we have all those features we saw before. This is what is the average price of the 50 closest apartments. So very intuitive feature, very similar to what a human would do if they were trying to figure out how an apartment should be priced. And you can see this performs the best. So going from our standard set of features, this is what happened when we did that arbitrary kind of neighborhood encoding. This is what happens when we use nearest neighbors. So you get the best performance. At least I was able to get in the 3 days that I built this. Better handling, oh yeah. This is something I never talked about before, but where this breaks down is on the outskirts. So as you can imagine, with any city, you'll have outskirts, so points on the outside boundary. So if you think about what this nearest neighbors is doing in this case, is it's saying all the points it's going to find are going to be really far away, right? And it doesn't really make sense to weight all these points equally. So a proper way to deal with this is to do like a exponentially decayed weighting, where the further the point out, the further out the point is from your listing, the less weighting you give to that piece of information. So this is something I would do if I had more time to spend on this. Yeah, and here's the setup. Again, this is the Zappa configuration for this feature. So you can see the reason I'm doing this in a separate function is this one needs more RAM. So you can see I've set the memory size to 3 gigabytes because this has to hold all those apartments in memory. It needs more. You could, in theory, just run all of your functions in the exact same Lambda function and just have different cron listings for them. But this one costs me more, so I don't want all my Lambda functions to be running on this same one with more memory. Yeah, so how did I figure out how to display it for users? I literally just copied what Google Flights does. How many people have seen this before on Google Flights? Yeah, it's a pretty sweet feature. So what does it do? I'm from Calgary, so when I was booking, it's actually the first time I noticed this, when I was booking my flights home, this graph came up and I was like, ooh, what does this do? And it basically tells you how well your flight is priced. And it tells you a bunch of other stuff too. So it tells you whether that is a typical price. It helps you visualize this on the distribution, so you can see it's actually on the upper end of expensive. And it gives you a sense of like, oh, I could probably wait a bit longer and get something a bit cheaper. It's a pretty useful feature. And yeah, if you think about it, like with any type of data product, users want context on it. Otherwise, they won't trust it, right? So think about if I told you $3,000, $3,250 is normal for an apartment price. You may say like, great, based on what? So think about wording it this way. $3,250 is typical for this type of listings. Listings with the same number of bedrooms, bathrooms, and similar square footage and location typically have price ranges between $3,175 and $4,200. So that is much more intuitive. That gives you context for why this algorithm is calling this thing typical. And there's other simple things you can do, like round your values. Don't give the illusion that you have this crazy amount of accuracy down to the decimal place, because you don't. And then yeah, give users an easy way to visualize this. This graph gives them additional context, right? Not only do we know it's typical, just like I showed in the previous example, we know that this is borderline expensive, right? It's almost at that upper end of the distribution. And yeah, you don't need a designer to make this for you. I literally built it using this plotting library called matplotlib. If you go to my other presentation for PyCon, you can actually see the code I used to create this, but I took that out. So that's what that looks like in the Slack app. So you see all the things I showed you before. Price is high, gives you context on how that was calculated. Cool. How are we doing for time? We're at 8.
Go ahead.
Okay. I don't know if, hopefully this part will be interesting to people. So with any application, you want to know, is everything going as expected? And most, what you absolutely need is you need something that says like, are my functions running and are they erroring? Are they running successfully? But that isn't really sufficient for me. So this is a really messy, data-heavy application where things could be running just fine, but under the hood stuff is changing that I'm not aware about. And so in order to do this, like if I really want to know, is my thing working the way it should, I need to look at the data. So for example, am I getting the expected amount of listings each day and from each source that I'm getting them from? Am I seeing the expected amount of missing values in each column, right? So because I'm pulling this off of other websites, I am prone to whatever changes they make to their websites or how their websites work. So if all of a sudden I'm seeing, square footage is null for every single apartment, that probably signals that something's fucked up and either my code is wrong or something on the website changed and I need to do that. So typical application monitoring will not detect this for you, right? Your function will run because it is possible for square footage to be missing, right? A person can just not put that on the listing. These types of things are really hard to detect. With my model, I want to know, is my model performance in line with expectations? And I'll talk about that a bit later. So this is where this library called Great Expectations comes in. And it's pretty neat. I came across it, I think about a year ago. And basically what it is it's a framework for writing tests for data. So they have this concept of expectations, which is very intuitive. What are properties you expect of your data? And basically what Great Expectations lets you do is say, here's a data set, here's my expectations, validate, does data set meet those expectations? So examples of where this gets used is like if you have a heavy data pipeline, you could put this at the beginning of your pipeline to check the inputs. You could put it at the end to make sure all your transformations ran as expected. If you have a machine learning model, which is very sensitive to the type of data you're feeding it, you could put it at the beginning of that. Or in my case, you can run it periodically on a schedule to keep doing sanding checks on your data. They have a ton of different types of expectations. So you can do things like check if your column has null values in it, if it matches a regular expression or a set of expected values. Values are unique. You can make sure you have a certain amount of rows, a bunch of things. I won't go through them. What I will show you is a very simple, motivating example. So here is new listing counts going into my database, right? So this is October. You can see it's oscillating around, I don't know, like 900 on average. It's a big dip here. Guess what? People like to celebrate Christmas and the holidays with their families, so they're not posting apartments. So that's why there's this drop and then it's back up to normal, right? So a very simple check I would do to make sure my thing is running is say that like, hey, I should have a minimum amount of listings going to the database each day, a couple hundred. So Great Expectations lets you do exactly this. I can say, hey, here's that expectation I showed you before. Expect table row count to be between. So I could spend a minimum. I could specify a minimum value. I could also specify a maximum value. I don't need that for my case. And then how you actually do this in Python is I'll have a SQL query which queries all listings from the last day. I will use their helper functions they have. So I'll create this new data set using the SQL query. So this will automatically pull the data, and then it will validate it against this expectation sweep. And then you get these validation results. So if it's a success, you can do nothing or log that somewhere. And if it fails, you can do something like send yourself a Slack message saying, hey, something's up, this check just failed. Here's the context, you had a minimum value of 500 and you only saw 225. You may want to look into that. So that's a very simple example of how it works. If we think about model monitoring, this is a much more complicated one, but if you think about how I've set up price rank, I've said that 50% of listings will be normal, 25% will be high, and 25% will be low, right? So if the model is properly tuned and it's working, is I should keep seeing those distributions over time, right? If all of a sudden apartments get way more expensive and my model's not accounting for that, we may see a shift where more than 25% on average are being called expensive, right? So that's something I'd want to detect and be alerted about. I don't have to keep looking at that. So this is, I don't have a code example for this, but this is something you can also do with Great Expectations. You can set distributional checks, so it can automatically detect if you have a shift in the distribution, which would alert me that something may be up with my model, and I probably want to dig deeper. So that is an alternative way you can do application monitoring. I think it's kind of interesting. You're just looking at the data that you're associated with your application. You're not looking at the logs or any of that. Okay, what could go wrong? Gotchas and workarounds. First one, remember I talked about cold starts and warm starts? So when you're doing a cold start, so for the very first time, AWS will run all these import functions, so import all your modules, and then this is the code that gets invoked that will actually run. So this runs for the first time, these imports, and then every other request, so when you have a warm Lambda container, these never run again. So what that means is these are all shared objects across all those invocations. So session, a common thing you do is you'll instantiate a database connection once, and then you'd share that. What could go wrong? Say one of the transactions fails on your database. All subsequent transactions and other invocations will start failing as well. So if you do some Googling, you'll stumble upon, there's a good blog post written by this guy. Basically what you do is you add this decorator function on every function that runs with a database call. And what this does, it'll throw a try except, so it'll try and commit your transaction. If that doesn't work, it'll make sure the rollback is always called. So then your transaction gets reset and all the other functions will work properly. So that was a gotcha for me. Another one was this slim handler killing my performance. So remember I talked about slim handler and I said what it does is it sends all your big dependencies into S3, and then on cold start, it actually has to pull all those down. So it has to download this 100 megabyte file and unpack that into the temp directory. For a warm Lambda function, this is fine because it does that once on the cold start, and then all the subsequent invocations, it doesn't redo that step. So it works fine. However, when traffic spikes, AWS auto scales. So it'll start spitting out more and more Lambdas. And when it does that, each of those Lambdas is then going through the cold start, which is now really slow because of the fact that it has to pull down this big package. So that's where things kind of fall apart. And to get around this, I did something kind of hacky, but it also highlights something cool about Zappa. So Zappa has this interesting extensibility where it lets you, in your configuration file, it lets you call arbitrary Python functions at different points in the deployment. So in my case, I can call an arbitrary Python function after it creates the deployment package. So that's what I did. So I built a Python function that, that literally, I do want to go there. It will literally, after the zip package is created, it will remove any files that match these regular expressions. So it'll remove those heavy libraries like pandas, scipy, numpy, all that stuff. And then it will upload that smaller package. Again, this is a problem for me because I have a monolith. It's one repo, which is doing all these things. So I don't want my web application to have like pandas and numpy and all that stuff. It doesn't need that. It's literally just the price rank function, which runs on schedule, that needs numpy and pandas. So for all those other functions that don't need it, I can remove all those large packages, and then they don't have to use Slim Handler. So that was another workaround. I wrote a blog post on this if you're interested in reading. Third one. I talked to you before about how certain Lambda packages, or certain Python packages have compiled dependencies, and if you want them to work on your Lambda, you need to swap them with a package that was compiled for Amazon Linux. Zappa, or the Rich Jones guy, Miserloo, who wrote this, he built his own library called Lambda Packages, which has all these packages pre-compiled, but I think similar to Zappa, he must have just called it in and stopped working on any of this stuff. So you can see there's no new packages getting added since 2018, which is a problem. As soon as you want a different package that's not available. So how do you get around this? You can use Docker, or what I did is spin up an EC2 instance with the Amazon Linux AMI. You'll build a Noi on there, and then you'll pull it down. So you'll build a package that has all the compiled dependencies properly set up for Linux. You'll then save that in your repo. And I did this super hacky thing, but it works, where I saved it to my directory, I renamed it Lambda Noi, and I just do a try except for the import. So if I'm running locally, this will work. It properly imports the package that was compiled on my Mac OS. If we're running on Lambda, this fails, and it falls back to importing that pre-compiled version. So pretty hacky, but it works. Workarounds in long term. I think I talked about before how they're planning on adding support for Docker. So eventually you'll be able to build those deployment packages locally with Docker, which will solve all that. It won't be trying to look for a pre-compiled version of it. It'll just build those each time. And there are actually workarounds available for you to use that today, but it's not natively integrated. Cool. So wrapping up very quickly. What's great about serverless? Zappa and serverless let me focus on differentiating factors, right? That is the beauty about this. It abstracts away all of that stuff you don't want to worry about, and it lets you just write code. So I don't have to worry about AWS configuration headaches, no API gateway, configuring elastic load balancers, none of that. Just write code, have fun. And that's it. Thanks for listening. Questions?
It's a question. Can you go back to the slide where you use the ANN result in the Quantile feature?
Say that again, sorry?
So can you go back to the slide that you use the ANN result in the Quantile features?
Oh, Annoy, that part, yeah. Where was that? This part here? down.
No, I think they get this one. So like you're taking like the average of 50 points.
Yeah.
Okay. Now this is a continuous number. Do you actually create some catalog and bin it rather than actually just use this number in your feature?
No, I calculate this. So each time the model runs in batch. So what it will do is it will run. I'll retrieve the nearest neighbors for each apartment live. So I'll fetch them against all listings in the database.
What I mean is like this number is can be basically it's a continuous number.
Yeah.
Yeah. So like do you need to do anything like before you?
Oh, like capping or scaling or I don't think I did. You could look at the distribution and figure out a way to. Some of these features you need to do capping and flooring, like size. Like some people will write that their apartment's like 100,000 square feet, which is dumb. No, it's not. So you do need to do some feature cleaning on these variables. I didn't talk about that, but I don't think I did anything for the nearest neighbors. You can also just do a median instead of an average. I tried both and it didn't make any difference. But that's a way you could get around the outliers. Good question though.
Thank you.
Next. Okay.
Sorry, could you tell me how you cluster based on the Google location? I mean, based on what?
Yeah. So neighborhood. What I was saying is that I didn't use Google. What you could do instead is Google has an API, I don't know what it's called, but you feed it a latitude and a longitude, or you can maybe give it an address, and it will return a bunch of information about that address. So one piece of information to return is what is the neighborhood name. Call it entertainment district, right? So how you would put that in a model is you do have you heard of one-hot encoding? One-hot encoding? I can't remember your background, sorry. One-hot encoding. You basically create a binary indicator. So instead of having cluster 0, cluster 1, you'd have a feature that said entertainment district. And for all the apartments that fall in entertainment district, you put a 1, and otherwise you put a 0. So that's how you do this encoding. So it's the exact same thing with these arbitrary clusters. They're the same. Does that make sense? Okay, cool.
Next. So since you're sharing everything, is the code available on GitHub?
Yeah, it's private, but
Are you
I can
violating any terms of service with Kijiji?
probably.
I think this is super relevant for thinking about more here. I think we mentioned at the beginning, just as last time the post, there's overbilling sometimes. Oh, in my training, did you say that?
Yeah, no, I said that. Yeah.
So, would there be a way of, first of all, is there backend data out there, and would there be a way of working it in? That's my first question. And B, would there be some kind of rats in the neighborhood index that you could use? I'm sure you'll try with points now.
Neither of those data points exist. So, yeah, it's Kijiji. They don't publish what an apartment eventually went for. That would be cool. You can get that with home prices. So they've started releasing this was a big deal. I mean, you guys are probably aware of this. What was it? December? Was it 2019, 2018?
2018, yeah.
Yeah.
Report with Supreme Court of Canada.
Yeah, so 2018, realtors are now allowed to show sold prices on their site. So you can imagine that would also be useful for this. How you would bake that into your model, I would predict if I had a sold or what do you call it, contract price for every apartment, I'd fit my model against that. That's what people care about. Actually, no, sorry, that's bad. I take that back. I don't know how you would do that. If I was in the home situation, you'd probably want to predict what is this home likely to sell for. I guess you could bake that in. I'm not totally sure how I'd incorporate that, but yeah, good question. And yeah, no, raccoon index would be another good one. I have a couple of those hanging around my house.
The city has open data for that kind of stuff.
For rats. Nice. Nice. Yeah, I bet if you put does apartment appear in building with reported bed bugs, that would probably drive the price down.
Next.
I might have missed this, but the Great Expectations thing, where is that being run? Like, where does the checking happen?
I run that in Lambda as well.
Okay.
Yeah.
Okay.
So ultimately, if like the Lambda function that's running Great Expectations fails, that you still need like your typical application monitoring that like makes sure your things are running. The whole point with Great Expectations is like, what if everything's running and something else is changing and I'm not aware of it? So yeah, it's just like any other of those things you saw. I have a cron job, it's a Python API, you run it. Yeah.
Next question. So, okay.
Yeah, you bring me to it in terms of the insertion. But those rules against your database,
Sorry, say it again.
the expectation validation rules against your database.
Yeah. So yeah.
Okay, and is your database running in AWS as well?
Yeah. So it's RDS. RDS stands for Relational Database Service. So it's Amazon's like hosted database service. So I have it running in there, and it would run queries against that. You can also like do Great Expectations against like files. It supports a bunch of different computational backends. So in this case, like the checks are it'll compile all my expectations into SQL queries and run those in the database. So the Lambda function that runs Great Expectations is really lightweight. You could get away with like 100 gigabytes of RAM. So all it's doing is executing SQL queries and getting results back. But you can also do it with like pandas. So if you have files on disk, you want to validate those, Great Expectations can run all your checks using pandas. You can also use it with Spark, a bunch of things.
Yeah. One last question is regarding the Slack app. Do you need a Lambda as well for that to handle the UI?
So no, that's the beauty of Slack is I don't want to build a UI, right? You saw how much my form sucked. So that was the only UI I built. Everything else is just Slack. I guess we can. So Slack has an API. We could Slack. Like Slack has an API for where was it? Here. Like, you see this? Yeah. This is all built using the Slack API, right? So it lets you put in a title block. And I put in like different hyperlinks. It lets me attach an image. This is just like text and emojis. So there's no like UI. I mean, there's design and like I have to figure out how I want to lay this out. But there's no. I'm not writing like you're not doing any HTML or JavaScript or anything. If you just Google like Slack API for posting messages, they give you a bunch of examples of like different types of messages you can post just using the API. So there's no UI for this component.
My question was rather if you need a specific Lambda to accommodate the output of your APIs.
Yeah. So I think with Slack, you need to have a specific endpoint on your application that's registered, that's listening for API requests from Slack. So in my Flask app, I have a separate endpoint which handles all requests that come from Slack. Does that answer your question?
Yeah.
Okay, cool.
Next. Last call. Okay, so big fun. We got one more.
Have you tried any other model against your data, like XGBoost or something?
No, I didn't. I literally like whipped this together pretty quick. Good question though. One of my next things I would do on this, there's a variant of, I think it may actually be XGBoost. You can do Quantile Regression in that as well. I was gonna try that because it's more flexible. It handles like non-linearities and stuff better. So.
And one more thing, actually, pictures are also important.
Yeah, no, that's on the backlog too. I have a pretty busy day job, so I don't get a lot of time to do this.
Okay. Last question. Okay, so big thank you for doing this. This is amazing. Before we have like 10 minutes or more for mingling. Before you go, I would like to do the draw. Henry can do that. But as you can see, like this is the reason I love serverless. There is so little serverless technology, and how much business value Ian was able to do it. We were not teaching you about some functionality of services. It was net new. So he was driving the car without caring what's under the hood, like a little bit, but it's amazing. So thank you. I hope
I'd
to
like
see
to,
you.
until you run into some of the like corner cases, but
Yeah.
for the most part, it's really great.
Thank you. Hope to, so please volunteer to talk again. I hope to see you again.
Okay.
So let's do the, everybody has a raffle ticket? Okay, so you do the first one.
Yeah.
Let's see who's the running. And if you win, it's okay too.
Drum roll, please. 00303 448. Close.
Lovely.